Hello everyone! Hope everyone had a great weekend! Recently we learned about molecular orbital theory and how to figure out orbital diagrams and use them to calculate bond order. Let's take this methane molecular as an example. If we filled out the orbital diagram, it would look something like this. I want that.
With hybridization, we can reorganize the s and p orbitals into the same energy level and redistribute the electrons among them. Instead of 2s and 3 2p orbitals, we now have 4 sp3 hybridized orbitals, each with an electron of their own. Each of these orbitals has 1/4 s character and 3/4 p character, since they are made of 1s and 3p orbitals. By hybridizing, we lower the energy level of the 3p orbitals, thus lowering the energy of the entire molecule. The new orbitals are ready to bond with 4 hydrogen atoms, forming 4 sigma bonds and creating methane with a tetrahedral geometry. Let's take a look at ethene here. Here we can see that only 2 of the p orbitals have undergone hybridization, leaving us with 3 sp2 orbitals and an empty p orbital. This allows the atom to form 3 sigma bonds and 1 pi bond. That's 2 bonds to hydrogen atoms and 1 carbon-carbon double bond. The resulting ethene molecule has a trigonal planar geometry and a 120-degree bond angles. Let's look at acetylene over here, with linear geometry and 180 degrees of bond angle. Only 1 of the p orbitals has hybridized, creating 2 sp hybridized orbitals and leaving 2 unhybridized p orbitals, all ready to form pi bonds. This leads to 1 single bond, a sigma bond, and 1 triple bond, 1 sigma, 2 pi bonds. Now, for more information about the lengths and strengths of bonds. More bonds means more shared electrons, which means increased bond energy. More bond energy means a shorter and stronger bond. Hybridized bonds have S and P character. The greater the S character, the closer the nuclei are to each other, the shorter the bond. Rotation and rigidity. 2 carbons with a single bond can rotate freely, but 2 carbons with a double bond cannot. This is because sigma bonds are cylindrically symmetrical and remain intact when the bond is rotated. But pi bonds have indirect overlap and cannot be rotated without breaking the bond first. This is a very unfavorable process. So sigma bonds can rotate, but pi bonds cannot. Carbonyl hybridization. Here we see a molecular orbital diagram of a carbonyl. Notice the sp2 hybridization of both the carbon and the oxygen. Now see the electrons filling in the orbitals. Once the electrons have taken their places, we can see that a sigma bonding orbital is filled, and so is a pi bonding orbital. 2 unhybridized pi orbitals remain. The antibonding orbitals are unfilled. We know from our later studies that carbonyl carbons are very reactive. Why is this? Well, I'm glad you asked. The electronegativity difference allows the oxygen to hold on to more of the electron density in the sigma and pi bonds. Because oxygen is holding that extra electron density, it is closer in energy to the pi bonding orbital. It has a partially negative charge. The carbon, on the other hand, has less electron density. It is closer in energy to the pi antibonding orbital and has a partially positive charge. This creates a dipole, making the carbon very reactive.
Well, Sabrina, what have we learned today? I learned that sp3 hybridized molecules are tetrahedral and have a 109.5 degree bond angle and involve 4 sigma bonds. sp2 hybridized molecules are trigonal planar and have 120 degree bond angles and involve 2 single bonds, 1 double bond, and 1 remaining p orbital. sp hybridized molecules have linear geometry, a 180 degree bond angle, and involve 1 single bond and a triple bond and 2 remaining p orbitals. The shorter the bond, the stronger it is. The greater the S character of a hybridized bond, the shorter and stronger it is. Sigma bonds can rotate without breaking, but pi bonds cannot. A carbonyl is a hybridized bond with a diploid that makes it very reactive. Great job, Sabrina. Thanks.